Thank you very much, Giovanni. Thank you again for this kind invitation and to give me this opportunity to share with all of you some of our recent experimental work. So I entitled my talk Ferrimagnetic spintronics because I want to show you two recent works. One where we use cobalt terbium ferrimagnetic layer on top of tungsten, and we exploit the spin Hall effect of tungsten to show the spin orbital switching. And in the other, more recently, where we exploit the cell production of spin current in magnetic materials, in particular ferrimagnet, where we have a strong spin orbit coupling to the 5D band of this rare earth, in this case with gadolinium iron cobalt. So let's remember that the main operation in recent spintronics advancement is the spin charge current conversion. And this happened. And this happened in bulk material due to the spin Hall effect. So if we inject a charge current, we generate a transversal spin current or a spin accumulation at the edge of the nanowell. The field of merit or efficiency of this spin charge to spin current conversion is called the spin Hall angle, and has been studying many material. I think the material most studied was or is platinum. And thinking in technological applications, thanks to this pioneer work in 2011, where we sweep in-plane current in nanowire of platinum, we can switch the perpendicular magnetization of this cobalt nanodot. And I also contribute to this similar experiment in the case of platinum cobalt nickel system in this work, in my former position. And it's turned out that the switching with the electrical current or charge current is quite fast. So this is also very attractive for application. It's below 1 nanosecond. And recently, in our team here at the German Institute in Nancy, in a project led by John Gorchon, we have shown that even we can, using a photo switcher, we can get the switching of just a few 6 picoseconds. So this is the outline of my talk. As I already mentioned in the first part, I want to show you the advantage of this system, quite robust, tungsten cobalt terbium, where we exploit the spin Hall effect of tungsten to get the switching of perpendicular magnetization of cobalt terbium. And in the second part, where we can use amorphous ferrimagnet materials to show a large cell production of spin current and that we call cell spin orbitor in this gadolinium iron cobalt copper system. So let's remember, I think you all know, but let's remember some characteristics of this rare earth transition metal ferrimagnet alloys. So we have two magnetic sublattice, one given by the rare earth and the other by the transition metal, and they have different temperature dependence. So as a consequence, we have some characteristic temperature here showing this blue curve. So when the net magnetization vanishes, we call this magnetic compensation temperature. Slightly higher, we have the angular compensation temperature because the relationship between magnetization and angular moment is given by the zero magnetic ratio, which are different for the rare earth and transition metal. And if we increase even more the temperature, we reach the Curie temperature. Above that, the system is no longer a ferrimagnet. So this is something very well known, 40, 50 years, these three characteristic temperatures. But just recently, there is a theoretical paper in this group by Richman and co-worker, where they showed theoretically that could be some cell production of spin current driven by magnons in this amorphous ferrimagnet. And I stresses this kind of characteristic temperature, that this cell production vanishes when we reach this condition, dm dt equals 0. So it could be something like here in this blue curve. And I will come to this to compare with my experimental results. Now I move to our system. We grow by spattering 3 nanometers of tungsten and then 3.5 nanometers of cobalt terbium with different composition, and we cap this with 3 nanometers of aluminum, with this naturally oxidized. The advantage of this cobalt terbium, despite that it have a strong perpendicular anisotropy, is that it's easy to integrate on either any system, 3-dimensional, bidimensional, while keeping its magnetization perpendicular to the plane. So we can tune the the net magnetization of the system, and when the net magnetization is dominated by the terbium magnetic sublattice, we call the system terbium rush phase. When it's dominated by the cobalt sublattice we call cobalt rich phase, and at the point where we cancel out each other, I mean the net magnetization vanish, we call this magnetization compensation point. We can get this similar tuning of magnetic or net magnetic moment by temperature. Here, for example, in a whole bar, I mean, electrical detection is much more sensitive than the magnetometry. And here that we can see is a different temperature, the anomalous Hall effect on this tungsten cobalt terbium system. At 300 Kelvin, we can see here one sign of the field-induced switching, and at 350 Kelvin, we see the opposite sign. And about 320 Kelvin, we don't see any cycle. So we can remember this this feature on this system. When the system is terbium rich, we have one sign. When the system is cobalt rich, we have the opposite sign in this field-induced magnetization switching. And where we don't see the cycle here, it means that we're above the magnetic compensation temperature, in this case 320 Kelvin. There is some approach, some methods to estimate the angular compensation temperature. One of the more recently is reported here in this nice work by King and Professor Teru Ono in Kyoto University using domain work propagation. So let's continue with the characterization in our series. We have a different composition, and this is a room temperature result of magnetometry. In the left, we show the coercive field, and in the right, the net saturation magnetization. And we can see that the coercive field tends to diverge, while the net magnetization tends to zero at this magnetic compensation point. Once again, as function of temperature, here the results on this particular composition, the coercive field here, the blue points, and we see that a decrease when we increase temperature is the typical 1/T in magnetic material. But when we start to get close to the magnetic compensation temperature, coercive field start to increase, to diverge, and then after the magnetic compensation temperature, decrease much faster. And I want to highlight the feature here. So below this magnetic compensation temperature, we have one sign of this loop, of this field-induced magnetization switching, and about the magnetic compensation temperature, we have the opposite sign. In this case, this is 300 Kelvin, and this stands for 270 Kelvin. Now, I want to show you our main experiments. So in the left, once again, the field-induced switching. This is two cases of one is cobalt 76, the other is cobalt 78. So at room temperature, this is terbium rich, and in the bottom is cobalt rich. Here we use a little current, 400 microns. Now that we show here in the middle and in the right is our main experiment. So instead of your sweep perpendicular field, we sweep here in plane pulse current with this characteristic. And that we can see here is that we observe a nice cycle, nice switching, very sharp here. The full amplitude here and here here we have the same amplitude, so we get 100% of magnetization switching. If we reverse the in-plane field, we still need a little in-plane field to get the spin orbital. We reverse the switching polarity. All this agree with the we expected for a spin orbital induced by a Soin Hall effect. So, I mean, we were quite happy with that. And now if we look here in the top, this panel, this is for the case of terbium rich sample. Okay, this is nice. We observe the current in the switching, it's sharp, the 100% amplitude change when we change the in-plane field. However, there is something unexpected, because here that we observe is the opposite switching polarity. It's something like here for the terbium rich. And so the question is, what is the origin of this? What is the origin of this difference? We were wonder. I mean, many explanations about that, and one could be thermal contribution. So for that, we redo this kind of experiment, but instead of using little current, DC 400 microamp, we will use pulse current. And this kind of anomalies or unexpected behavior happen in our world series. Here you see the 4 samples that are terbium rich at room temperature have the same switching polarity that the cobalt one. When here is expected the opposite one. So here is our experiment that I was talking about. So instead of using little current, we use pulse current between 5 milliamp and 34 milliamp. And that we can see here is that a low current will have one sign of the switch of the field-induced switching polarity, and about 20 milliamp we have the opposite sign. So that we can see here is that about 20 milliamp we heat up the sample above the magnetic compensation temperature. And if we look now at the switching cycle here with current, the critical current to switch this magnetization is about 24 milliamp. So it's well above the current where we have more or less the transition. I mean, this stands for the magnetic compensation temperature. So now we can understand this unexpected behavior, and we can draw some conclusion. So during the switching experiment with electrical current, we bring the device, the sample at a given temperature below the Curie temperature, because here we can see that even at 54 milliamps above this critical switching current, the sample still is magnetic and with perpendicular magnetization. And it's about the both magnetization temperature, magnetic and angular. Here is the magnetic. I will not enter into detail about the angular calculation. And above the initial temperature that we can set in our cryostat. So now we understand that, but we can further study this at a different temperature. So now we take the same device in our cryostat, and here in the top, we perform the current induced magnetization switching at different temperature. Here we show just a few ones for sake of clarity. And in the bottom, we show now also the longitudinal resistance, the resistance of the channel where we get the current. And that is very surprising and interesting is that you look here at this vertical dotted line where we have the critical current or the switching current, we reach a given value of longitudinal resistance. And it's the same. So despite the cryostat or initial temperature in our experiment, the switching happened at the same resistance of, longitudinal resistance. And a value of longitudinal resistance is a value of temperature. So we have the same value here of longitudinal resistance, means that we have the same temperature. So that was very surprising for us, and it's a characteristic temperature that we call temperature switching. And is to estimate once we perform temperature dependence of this longitudinal resistance with just little current, 400 microamps again, and we extrapolate the linear behavior because due to technical limitation we cannot reach higher temperature here. We can estimate this temperature for this concentration of cobalt. And here is the question. I mean, it's still an open question. The physics behind this behavior, this characteristic temperature, and I wonder if this relates with this condition given by this theoretical paper, where we have that the cell production of spin current in this ferrimagnet is vanished, driven by magnets is vanished. But experimentally, it's not so easy to estimate because the magnetic signal in a ferrimagnet is weak, and even in a few nanometers is weaker. So at the beginning, naively, I thought was easy or straightforward to estimate, to make the relationship experimentally, but it's not the case. We're working on that. So before to come to my conclusion of this first part, let me acknowledge all my collaborators in Nancy at Janamon Institute and in Grenoble and Spintec, and especially my former PhD student, Taya Fang. Now she's back in Vietnam. So here's the summary of the first part of my talk. I wanted to show you that this tungsten cobalt stereo system is quite robust. It's very reversible. I mean, we overcome the magnetic compensation temperature, but we repeat the operation many times after several months or over a year. And the device is very, the cycle is very reproducible. And here we have a change temperature and composition, and we can get this kind of phase diagram where we show this characteristic temperature, the switching temperature, and increase when we increase cobalt as Curie temperature, and opposite that magnetic compensation temperature, which decrease when we increase the cobalt concentration in this cobalt terbium ferrimagnetic alloy. The switching current density is on the order of 10 to 11. That is normal for spin Hall effect material, and that is very also was surprising that we need just a little in-plane field down to 2 millitesla That was surprising because cobalt terbium has a very strong perpendicular anisotropy. And at the beginning, I saw that we need really high in-plane field, but in tungsten cobalt terbium was not the case. It's the different behavior. We have not reported our results, but we have also studied platinum cobalt terbium bilayers. And in this case, because most of the current flow in platinum, we don't hit strongly cobalt terbium, so we need more in-plane field to get the spin orbital switching in this bilayer. So, I mean, this bilayer, my message here is quite robust, very reversible to get the spin orbital switching in this tungsten cobalt terbium. So that's what my message that I want to show you in this experimental work in the first part. Now I move to the second part. In this second part, that I want to show you is that magnetic material, and particularly ferrimagnet material, are very efficient to cell production of spin current and that we call cell torque or cell spin orbital. And I will show you in this case gadolinium iron cobalt copper, and I will compare, for example, with platinum copper. So let's remember the symmetry of the case of the spin Hall effect, and this happens not only in non-magnetic material but also in magnetic material. So when we inject a sharp current, we generate a transversal spin current with a spin polarization perpendicular to both the spin current generated and the sharp current injected. And the field merited, as I already told you, is given by this dimensionless parameter, called a spin Hall angle. It's happened that in magnetic material, we have another symmetry of a spin current generation. And in this case, we keep the name given by this pioneer work by Taniguchi, Grolier, and Stiles, where here the spin polarization of this spin current is parallel to the magnetization of the magnetic material. And the efficiency is given by this spin anomalous Hall angle. So we have these two symmetry in a magnetic material, one given by the spin Hall effect and the other given by the spin anomalous Hall effect. In the recent year have been more theoretical works, and I will not enter into detail, just to mention that we can summarize these two symmetries as we have shown here in this work recently published. The spin current generation in a magnetic material, we can consider with two symmetry. One, the spin Hall effect lie, where the perpendicular, the spin polarization of the spin current generate is perpendicular to the magnetization, and the other, the spin anomalous Hall effect lie, where here the spin polarization of the spin current generate is parallel to the magnetization. So if we have this condition here, I think it is not hard to understand that we cannot generate any torque or cell torque on its own magnetization because both are parallel. So we can summarize this part as it's showing here. We have a magnetic layer. When we inject a sharp current, we have two symmetry. One given by the spin anomalous Hall effect, which cannot generate cell torque, and the other given by the spin Hall effect symmetry, because they are perpendicular, we may generate cell spin torque. But what is the condition to get this magnetization switching here? If the spin current emitted from this magnetic material is absorbed outside the magnetic layer. So for that, we need a good spin sink. And that's I will show you in the last part of my talk. Actually, in the community, there have been already several experimental work where they have shown switching in single magnetic material. In this case is iron platinum. Even that in one case they say it's due to gradient composition, in other there is no gradient composition. Also in cobalt terbium here, I wonder if this could be explained, for example, by the theoretical work that I mentioned in the first part of my talk, with the cell production of current driving my magnum. And in permalloy have been shown not the switching but the spin orbital, also by spin torque or spin pumping in single nickel iron alloy. So that I want to show you is in the following, that if we have this, if we fulfill this condition of having a good spin sink, we can enhance the cell torque in our case in gadolinium iron cobalt copper. First, I will show you the quantification of the overall efficiency, spin anomalous Hall effect plus spin Hall effect. And for that, we have shown the following technique based in ferromagnetic resonance. Spin torque ferromagnetic resonance, and here a micrograph of one of our devices. We inject AC current using a RF source through a bias tee, and we use locking detection. But in addition, we will add a DC bias current to do the modulation of the line width. And actually, we have shown, using similar this technique, several studies in the recent years, for example, in flexible substrate, in highly epitaxial system, or in this permalloy iridium manganese antiferromagnet. Here, our main system, this three-layer, gadolinium, iron, cobalt, copper, and permalloy. So we can see here a typical ST-FMR spectrum, and we see two ferromagnetic resonant modes. Due to anisotropy, it's not difficult to identify which is one. This corresponds to the precision of nickel iron, and this one to the precision of gadolinium iron cobalt, which has larger damping, and so the intensity heat is much smaller. As is happening here is that due to the current, AC current flowing in copper and gadolinium iron cobalt, when we reach the FMR condition, we may process the magnetization of permalloy. We can perform, for example, frequency dependence, and we can get typical, Kittel relationship. The blue one is for permalloy. This means that the plane is an easy plane for permalloy, but the thin film plane is a hard plane for gadolinium iron cobalt here. So this means that spontaneously the magnetization of gadolinium iron cobalt is perpendicular to the plane. If we plot the line width versus frequency, we can get the magnetic damping constant. And most of this measurement was performed with the help of my former internship student, David Cespedes, that now is back in Peru. There is different methods to quantify the spin Hall angle or the spin orbitor with this technique, but we will use one of that I believe is more reliable, the modulation of damping. This means that in addition to inject only AC current, we will add DC current and see how changes the line width of this nickel iron resonance. First, let me show you a control sample. This is a copper permalloy, and in the top the spectrum, and in the bottom the modulation. Actually, there is no modulation as expected. Now I show you the main system. Here, the three-layer with gadolinium iron cobalt copper. We observe clearly a modulation of the line width of permalloy, and this is one sample. This is other system, very reproducible. We can quantify that. It's really high, the value, 0.8, 0.7. So we check many times in different devices, and we grow later this sample to compare with platinum to be totally sure that this is reliable. And here we can see the result of platinum, nice linear dependence also as expected, but much smaller the variation than in gadolinium iron cobalt, despite that more current flow in platinum here. If we can quantify this, the effective spin Hall effect of platinum is about 0.03, like 25 times smaller than in gadolinium iron cobalt copper. So this is our first main results. It's really high. This is charge spin current conversion. And I think it's highly reported in any material using similar method. So some questions rise. This is the overall effective, but we believe we have both contributions, the spin anomalous Hall effect plus the spin Hall effect. Not all come from the ball. We have also interface contribution because we have rush-bar interface in this gadolinium iron cobalt and copper. I will not enter into the detail, but a way to disentangle this is with second harmonic, because with second harmonic we estimate the spin orbitor only the cell torque that is coming only from this symmetry, because as I already told you, this symmetry cannot give any cell torque. So for that we use second harmonic. I think it's very well known method also. We inject a current here and we measure the transversal voltage, and in this limit, and we have checked this condition, the planar Hall effect much smaller than the anomalous Hall effect in our system. The ratio of the linear behavior of the second harmonic over the quadratic factor of the first harmonic gives us the damping line or field light torque. I will focus on the damping line. And here, the main result of three systems, gadolinium iron cobalt copper with only copper, very weak signal, with tantalum, very weak, slightly positive, and with platinum, much larger, and here the slope is negative, opposite than tantalum. So that we say here is that, as already told you, with tantalum and platinum, we have a good spin zinc layer in addition to gadolinium iron cobalt copper. So we enhance in this cell torque. But of course, platinum and tantalum, they contribute to the spin Hall effect too. In order to analyze that, I will focus in the case of platinum. We can, it's not difficult. So we have the total damping line in the 3-layer. We say that we have a cell contribution of gadolinium iron cobalt copper, and we know that there is also contribution of the spin Hall effect of platinum. In our old sample of platinum, we have measured this spin Hall angle, so we can estimate the damping line coming only from the spin Hall effect of platinum, and we reach this value. So doing the subtraction of this total over the contribution of Hall effect, we get the cell contribution in this gadolinium iron cobalt copper, and it's quite large. It's about -510 to -10. It's similar to the most effective heavy metal. We can compute also the kind of the spin Hall effect in this system, and we can see that it's large, 0.16. So we have disentangled this from the total efficiency that we estimate using spin torque ferromagnetic resonance. Before to come to the end of my talk, let me acknowledge all of our co-workers, nice collaboration, especially our younger student, David, Eloise, and Aldo. Eloise now she's doing a PhD under our supervision. And allow me a little advertisement, so maybe you are also interested in oxide spin electronics. So next Wednesday, July 7, we are organizing this workshop. More information here. So with that, I come to the summary of the second part of my talk, the last part. So I show you that we have a giant effective overall efficiency in gadolinium iron cobalt, like 25 times in the case of platinum. And we were able to disentangle the contribution of both symmetry, and we have shown that using a good spin zinc, we get a large damping line cell torque. As a perspective, we are looking for switching without any external heavy metal, and also the Lorentz-Moria interaction production and Scormion motion. With that, I would like to thank you for your kind attention.